Good evening, Calculus 1 students. So this video has to be part of your lecture notes, okay? So it's not an exercise per se, it's part of the theory, but I want to keep the class time just to do something else, okay? So, but it has to be filled in. What we're going to do here is we're going to prove the power rule, but we're going to prove it only for positive integers, okay? So in other words, when n is equal to 1, 2, 3, and so on, okay? So first of all, let's review what is the power rule. It says that if n is a constant and x is just x, it's like the main variable, the input of the function. So if n is a constant, or if you have, let's say, a power function, that's what we call them, like x to a constant power, then to take the derivative of that, you need to drop the exponent in front and subtract 1 from the exponent of x. Okay? Where, as I said, where n, actually, the real power rule is that n could be anything, like could be any real number as long as it's constant. But as I said previously, we're only going to prove that rule when n is a positive integer. Okay? This video is going to be structured in two parts. First, I'm going to introduce a formula that will allow us to prove the power rule. Unfortunately, I will not prove the formula because it relies on material that we typically cover in Calculus 2. But I will justify it just by showing you a couple of special cases. Okay? And then after that, we will use that formula to prove the power rule. So here goes. So first, let's write it down. The formula, okay? It's a factoring formula, and it applies when n is bigger than 2. So when n is bigger or equal to 2, then we can factor out t to the power of n minus x to the power of n, which will be t minus x. And then we write first t to the power of n minus 1. Okay, so it's going to be at least 1, in other words. And then we decrease the exponent until the exponent of t is reaching 0. Okay? So in other words, we're going to have here t to the power of n minus 2. And each time we decrease the exponent of t, we increase the exponent of x. Okay? So then we continue like that until we reach t to the power of 1. And then x to the power of n minus 2. Plus, finally, x to the power of n minus 1, where you have to see here t to the power of 0, okay? So that is a factoring formula. Let's have a look at the cases, okay? So, as I said, I'm not going to prove this formula, but I'm just going to justify it for a couple of values of n. Like, I'm going to do it with 2, 3, 4. So for the case n equals 2, t squared minus x squared, okay? So you know this formula already. It's the difference of squares formula. You're going to have like t minus x, and then here you're going to have t to the power of 1. Okay, so here I'm going to put a little bit of color to help you. T to the power of 1. And then now t is already to the power of 0. So you're going to have plus x to the power of 1. So in this case, it reduces to the difference of squares. So I'm just going to write it down, actually, difference of squares. Okay? If we look at the case, n equals 3. So you're going to have t cubed minus x cubed. So if you try to apply the formula, what will happen is you will have t minus x, and then you start with t squared, okay? So 3 minus 1 is 2. And then you decrease the exponent of t, but increase the exponent of x, each by 1. So t to the power of 1, x to the power of 1, plus finally x squared. So you also know this formula. This formula comes from, it's the difference of cubes. There you go. Difference of cubes. Now, finally, if we go ahead and look at case number 4, and that's it. So case n equals 4. Now, something interesting kind of happens, but you will see that we will fall back on our feet. So typically, the way we factor this, like the way you have learned in high school, is to first factor it as a difference of squares. You will have like t squared minus x squared times t squared plus x squared. Okay? Then, this is factorable again. So this is itself a difference of squares. So you're going to write t minus x times t plus x times t squared plus x squared. The final step is to expand this bracket, okay? And as you do it, what you're gonna get is t minus x, and it's fairly easy to expand the bracket if you're careful. This is gonna be t cubed. Now, t times, actually, yeah, I'm gonna go here. X times t squared, so plus t squared x. And then you have here plus t times x squared. And finally, plus x cubed. So as you can see, the formula is also valid when n is equal to 4. Okay? Certainly, that's not the proof that the formula is true, okay? To prove that the formula is true, we need tools that are slightly more advanced. Okay, we could actually do it by expanding this side and getting that side, but the problem is that we need to take into account that we don't know exactly how like what's going to be there. Like, well, we do actually know, but the problem is that when n is really large, we cannot base our proof on that. Okay, now that we have this formula, let's go ahead and prove the power rule. Okay, so now I'm erasing this. But I will be using the formula anyway, so you'll see it back. Now, here's the proof that I start like, I'll do it in black, right? Proof. So remember that what x to the power of n, you have to consider this as a function. So we consider the function f of x that is x to the power of n. In this case, the derivative, so f prime of x, will be the limit as, and I will choose this definition, as t is approaching x, of f of t minus f of x over t minus x. The next obvious step is to replace f of t and f of x by what they are. So in other words, you have the limit as t is approaching x of t to the power of n minus x to the power of n divided by t minus x. So you get this. Now this is where the formula kicks in. Okay, so I'm actually gonna color code it so you can follow along. I'll color code it in blue. I think it's appropriate. So the formula comes at the top. You will replace the top by the actual result. So at the bottom, nothing's gonna change. So let's start just working out the top. You'll have t minus x, and then you will have t to the power of n minus 1. Then you will have plus t to the power of n minus 2x plus, and then you will continue like this until you reach t to the power of 1, x to the power of n minus 2 plus x to the power of n minus 1. All of this being divided by t minus x. at this point, remember that when you're solving a limit, and in particular a derivative, your goal is always to cancel a redundant factor. So you know right from the start that what you want to do is cancel this t minus x. Now you won because there's this t minus x here at the top that you can use to cancel the redundant factor. Once the redundant factors are canceled, you're going to replace t with x. Okay, so this is, remember, the direct substitution step. And as we do this, this is what we get. Okay, so every time I see t here, I will replace it with x. But I won't go too fast. The only thing I will do is the direct substitution, okay? So I have x to the power of n minus 1 plus x to the power of n minus 2 times the blue x. The blue x is actually a constant as far as this limit is concerned. Okay, so it's not replaced by anything particular. Then you have here x times x to the power of n minus 2 plus x to the power of n minus 1. Okay. Now, from there, another argument is that, okay, so let's have a look at the powers here. Okay. As I mentioned previously, every term, you write it from the preceding term by decreasing the power of, like, actually, let's go back to the t formula. Like, each term, you write it by decreasing the exponent of t by 1 and increasing the exponent of x by 1. So in other words, as t gets replaced with x, these all have the same exponent of n minus 1, okay? So what you end up getting is like x to the power of n minus 1 plus x to the power of n minus 1 plus all the way up plus x to the power of n minus 1 plus x to the power of n minus 1. Now, the last argument is, okay, fair. We have like a sum of x to the power of n minus 1. But how many terms do we have? Okay, to count the number of terms, what we need to see actually is, I'm going to erase this thing, and I'm just going to make pop out t to the power of 0 in front of it, okay? This will be kind of important, okay? So t to the power of 0, x to the power of n minus 1, okay? The reason I do this is because now I can count them. Look, 0, 1, 2, 3, 4, 5, until n minus 1. So how many is that? This is actually n terms. And this is because you're counting from 0. So be careful about that, right? How many numbers are there from 0 to 4? There's 0, 1, 2, 3, 4. You see? So there's 5 of them. Okay, so you need to be careful about that. So here's the argument. So we have here n terms. Since we count them from 0 to n minus 1, which means that we include 0 in our count. Okay, so that's why we have n of them. And this completes the proof. It means that instead of writing it as a sum, you can write it as a multiplication, n times x to the power of n minus 1. And this is what we wanted to prove. All right, I hope this helps. So we see each other in class. Remember that it's necessary to take this down as part of your lecture notes. But here goes. Have a good one.